Let me try.
This works, right?
Yeah.
Okay. Hey, it's great to have been in this and to be in this environment, in this winter school. I've learned an enormous amount, as you're going to see at the end of this lecture. I'm starting at exactly the end of lecture 1. We had a very simple setup. K is a number field. C is smooth projective curve over K. Genus 0 will hardly play a role in what we talk about. And we have a chosen K rational point, which I call E. I call J sub C the Jacobian of C. And we consider the injection of C into J sub C that sends any point in C to the divisor class of degree 0 there. We talked about the symmetric powers, the nth symmetric power of C. It's an n-dimensional variety. It's defined over whatever number field, whatever field C is defined over. And there's a natural map, which I call iota, to J sub C from that nth symmetric power of C to J sub C. And then we talked about the gonality of C. Now, the gonality of C is the smallest degree that C allows for there to exist a non-trivial map to the projective line. So if you're genus 0 and over an algebraically closed field, the gonality is 1, but beyond that, you're not going to get much gonality 1. Gonality 2 is if it's a quadratic extension of a projective line, hyperelliptic curve. And gonality plays an enormous role in what I want to call uniformity, or actually Mordell-Weil computation results. And we're going to see, we saw a bit of this, and we're going to see a little more now. There's also what I denoted by that collection of letters, SCKD, the set of K-conjugacy classes of algebraic points on C of degree D. So that's our setup, and we're going to have no more drinks, I guess, or maybe the reverse. Okay. So, as I said, gonality is related to uniformity, and the real reason for that is that there's a natural map of the set of K-conjugacy points, K-conjugacy classes of algebraic points of degree D to JC, and you get a map to the K-rational points of JC that way. And if the degree D is less than this gonality, you get an injection. If it's greater than the gonality, you get a surjection, and if it's equal to gonality, you get this absolutely amazing thing, which is it is what it is, and it would be really nice to give computations that describe it. Anyway, as I said, this is one of the great uses of Mordell-Weil, that is, say, to understand JC of K and such injections to control algebraic points on curves. So there's the modular curve. I'm giving you an examples of gonality. There's the modular curve y1 of n, and what it does is it classifies K-rational, well, if I'm interested in the K-rational points of y1 of n, it classifies points that are pairs EP, where E is an elliptic curve over K, and P is a K-rational point of order n. Now, as I say, here's a table of cube gonalities, which you can get from Martin Derricks and Mark Van Hoy paper. And the thing that caught my eye immediately was this one, the 31. N equals 31. The gonality is 12. But you have, if you have y1 of n or x1 of n and you map it to the projective line, you know that that map is degree greater than or equal to 12. And I say it's an impressive example. It's a curve that classifies elliptic curves with some torsion point, a fixed torsion point of order 31. Its genus is huge, 26. So that is going to suggest that it's very interesting test for the symmetric powers that map into it. Its gonality is 12. So for any number field, k, and any degree less than 12, you have this inclusion. So just imagine if j, whoops, did I messed up. I should be putting, okay. Sorry about that. I was instructed. There we are. Okay. We have the inclusion of the set of all k rational, the set of all degree d points of the curve over k maps injectively in the sense that two points that are conjugate map to the same thing, but otherwise nothing, into JC of k. And we're going to make use of that in various formats. But one thing I didn't mention in lecture 1 was the further development of the Mordell-Weil theorem. I talked a lot about Mordell-Weil, but there's Falting's version of the Mordell-Weil theorem, and it's really striking. It doesn't simply say that a curve over a number field has a finite number of points. It goes on to ask, but thinking of the curve in its Jacobian, it goes on to ask the more general question, what if you have a variety defined over a number field that's contained in any, not Jacobian, any Abelian variety over that number field? Apparently, it turns out that Vk is Zariski dense in V if V itself is a finite union of translates of sub-Abelian varieties defined over K. What does that mean? That means if you have any subvariety of an Abelian variety, the k rational points in that subvariety, the subvariety defined over k, the k rational points of that subvariety sits in something that is a finite union of points in that variety, a finite union of sub-Abelian varieties in that variety. If you go back to x1 of 31 and its situation, we'll discuss that much later. You will get an absolutely incredible uniformity statement. But of course, everything is not cheap. The proof is not constructive. It's tantalizingly semi-effective in the sense that even when you take the variety to be the curve sitting in its own Jacobian, Falting's theorem proves Mordell's conjecture. It says that that curve can only have algebraic points that are Zariski dense in a finite union of points in it, union of finite number of Abelian subvarieties in it, but a curve poor curve, not going to have too many abelian subvarieties in it, and so you get Mordell's theorem. The proof, oops. Yeah. The proof it doesn't give an upper bound for the size of rational points on C. It does implicitly offer a bound on the number of rational points, but with another, as I say, but, the bound is just incredibly high. I mean, it's not something that, so much is not something that can be used. But I don't know. I should ask the experts in the audience. Has anybody given I mean, we know it's an explicit, but if you have an explicit bound for something that's so large, nobody actually bothers to write and print the explicit bound. I don't know whether it is. Okay. Okay. So now I'll, so to speak, restate the uniformity consequences of Folting's theorem. So I have a curve, genus G, gonality delta. For any n less than delta, the set of k rational points of that symmetric nth power lies in the union of a finite set and a finite many translates of abelian subvarieties that lie in it. So as I say at the bottom, this leads to a challenging computational project. I mean, do we have interesting computational data on how often a symmetric power of a curve contains abelian subvarieties? It's worth giving a shot at it because I've never seen any explicit discussion of that. And now, in thinking about that and talking with people in the audience, I came up with this absolutely ridiculous definition, or terminology is ridiculous. But to give a sense of the strength of Folting's theorem, I'll call a curve non-nearly elliptic. That was just 2 days ago, and if I write these notes, I'll choose a better name. If the symmetric square of the curve contains no elliptic curve, even over the algebraic closure, it follows that the gonality of C is greater than 2. So C is neither hyperelliptic nor bielliptic. And Folting's theorem implies that C has only finitely many quadratic points over any number field for which it's defined. That's an amazing piece of uniformity right there. And if you have curves of higher gonality, you have even greater uniformity.
Did you move the left paper?
What?
Move the left line.
Oh, move this one?
Yes. Yeah.
Oh, where do you want? Oh, I see. Oh, I get it. Okay, thank you. Yeah, right. Okay. Yeah, I should have practiced this shuffle. It's a shuffle here. Okay. Small Mordell-Weil rank in the Jacobian of C. If you have small Mordell-Weil rank, you get precise upper bounds for a number of rational points. And what's amazing about it is this very, very simple, beautiful classical method of Chabot-T. It's been around for quite a while. It doesn't, it not only does not provide explicit upper bounds, as I've just said, as I've just underscored with my cursor, but it doesn't have the feel of doing it until Robert Kuhlmann came to its rescue. This is how it goes. It's very simple. You consider some topological completion, I call it gamma p, of the Mordell-Weil group of the Jacobian of C in the p-adic analytic group of QP valued points of the Jacobian of C. So you can think of the Mordell-Weil group as of C, the Mordell-Weil group of JC as being some finitely generated subgroup of this absolutely enormous analytic group, the p-adic points of JC, and you just take the p-adic completion of it, and you get a p-adic analytic group of dimension less than or equal to that Mordell-Weil rank of JC, because after all, it's completely determined by that Mordell-Weil group in a simple sense. And we assume this to be strictly less than the dimension of JC. So here's the picture. You have the curve. This is the ambient Jacobian JC of QP, this wiggly space here. And in it, you have the curve, well, the p-adic points of the curve in it, sitting as a sort of a nice one-dimensional piece, QP analytic piece of this p-adic analytic group. And you also have this gamma p, which is definitely, by hypothesis, less than in dimension, less than the dimension of this ambient p-adic analytic group. Now the C, whatever it is, the curve, generates everything as a group. So the C can't possibly be sitting happily in this gamma p, because gamma p is a group, and the C will never, be able to generate the whole group if the gamma p is smaller than the whole group. So you have an analytic situation where one analytic manifold, so to speak, intersects another analytic manifold, a one-dimensional analytic manifold, in properly, and you get finiteness, right? So now, if the intersection is finite, these are the p-adic points of C, then of course C of Q is also finite. So there we are. We get a finite finiteness of the Q rational points of C from this very, very simple geometric argument. Now it took Robert Coleman to reframe this approach to replace this whole picture that I gave a second ago, reframing as the construction of an analytic function on C whose zeros correspond to the intersection of C and gamma p. And therefore, if you have this analytic function and you understand it well, you can begin to make bounds, you can begin to make predictions, you're going to understand intersections. The intersections would be the zeros of a certain analytic function on C, p-adic analytic function on C, that you can compute to some extent. So for this, hyperelliptic curves form a very good collection of examples. A hyperelliptic curve, as I mentioned before, is something with gonality 2, and it's expressible as y squared equals f of x appropriately. And as I say down below here, this class of curves provides a wonderful testing ground for Diophantine equations. Okay. Now, we'll take C, such a hyperelliptic curve, assume it has a k rational point, and embed it via that point into its Jacobian. So GC is its genus, and RC is the rank of that Jacobian. And we're assuming that RC is not only less than the genus, which is what Chaboty would assume, but we might assume that it's sort of a little bit smaller. For example, here's a striking upper bound for a number of k rational points. It's due to Michael Stoll. If the rank is less than or equal to g minus 3, you have this staggeringly impressive bound for a number of k rational points. That is to say, for example, if the genus of the curve is 3, then C has no more than 67 points over any number field. You can go the other way. That is to say, the other way in terms of uniformity. You can ask how many hyperelliptic curves have few points. And here's a consequence of a result of Stoll and Mignon Yu, that if the genus is greater than 4, and the class of curves you're interested in are hyperelliptic curves, there are infinitely many hyperelliptic curves over K of genus G that have some, but no more than 41G minus 32 K rational points. Which, of course, is also a staggering bound. But what about hyperelliptic curves with lots of points? If the rank is greater than g minus 3, we have various examples. And I decided not to sort of run through all these examples in this in this lecture. So I have some time rather to describe the format of the really going technology that started from Chaboty. So I think of it as a three-stage thing. Chaboty began the game. Robert Coleman made Chaboty's game effective. One was always somehow constrained by having the rank less than the, we have unfortunately the rank less than the genus is an annoying hypothesis. Now, what is that genus, after all? It's not the genus of the curve, it's the dimension of its Jacobian. Now, what if you can increase the dimension of the Jacobian by producing a larger thing than the Jacobian? It might map to the Jacobian, but higher in dimension. And have that curve lie in that larger thing, and the poor Mordell-Weil rank is not going to change. So you get a lot of possibilities there. And that is the basis of what this new technology, it's a relatively new technology, and it has been effectively used in, it is the current technology of Chaboti, and this third stage is due to Min-Young Kim, who initiated it by defining this larger structure, larger dimensional structure, and the type of larger dimensional structure he produced for this he called Selmer varieties. Okay, I just want to give you one world's record. The world's record for curves of genus 2 with lots of points is held by an example discovered by Stoll 2 decades ago. It's this guy. It has at least 642 cube rational points. And if you think, the reason why I said 2 decades ago is one didn't have that much computational, is that right, Drew? One was, and when he did this in 2008, I should say, that last rational point, and it's only, is it the last? Yeah, it's probably the most impressive of the 642 rational points, came as a shocking surprise. So that's what number theory is? You know, that sort of thing. Okay. Going the other way, most odd-degree hyperelliptic curves have no over Q have no points, and there's again Stoll contributed to this, and there's this theorem of Poonen-Stoll that a positive fraction of hyperelliptic curves have only one Q rational point, the point at infinity, and there's a lower bound on this fraction that tends to 1. That this fraction, it tends to 1 of the genus goes to infinity. Okay. So recall that if C is projective smooth, we get that SIMD and SCKD are finite sets, that is, say, the set of all algebraic points on C of degree less than the diagonality is finite as long as either SIMD contains no translates of abelian varieties or the Mordell-Weil rank of JC over K is 0. And we can discuss x1 of 3, x1 of 31 again, and it's sim squared. I think one can prove that sim squared of x1 of 31 has no elliptic curve, and so therefore, if you imagine it as being an interesting example, you can say, take any, take x1 of 31 and consider all quadratic fields. How many rational points does, how many quadratic points does x1 of 31 have? And the answer would be finite. So it's kind of amazing that there are only finitely many quadratic fields that allow for elliptic curves with rational points of order 31, and that this is just the first example of a vast slew of interesting examples. I now want to pass to something which I like to call Diophantine stability. So here's the definition. If L over K is an extension of fields, and V is an algebraic variety defined over K, I'll let V of K be the set of K rational points of V, and I'll call V Diophantine stable for the extension L over K, or I might say L over K is Diophantine stable for V if V acquires no new rational points when one moves the base from K to L. That is, say, if the natural inclusion is an isomorphism. And the property of Diophantine stability of V is inherited by subvarieties defined over V. So how often is there such Diophantine stability? And I sort of messed up on this, but okay. Well, it follows directly from our discussion that if the Jacobian has model rank 0 over K, then C is Diophantine stable for all but finitely many field extensions of degree less than the gonality. And this is also true if SIMD contains no translates of Abelian varieties, or at least none with positive Mordell rank. Now, how often does this happen? Carl, Rubin, and I defined the notion of L Diophantine stability for L a prime number. A variety is L Diophantine stable if for every positive integer n and finite set of primes, there are infinitely many cyclic extensions L over K of degree that power of L, the nth power of L, that are completely split at all primes in S, and such that, and the conclusion of the theorem is that V is Diophantine stable for L over K. That is to say, V of L is equal to V of K. That is to say, for every positive integer n, and for L a prime, we'll call it L Diophantine stable if it has this amount of Diophantine stability, that is to say, no new rational points in that collection of fields. Now, we proved that if A is a simple Abelian variety over K, and all the K bar and the morphism of A are defined over K, then A is L Diophantine stable for a set of rational primes with positive density. Of course, we want more. We want the same to be true for a set of primes of density 1. Oops. Okay. I want to make a few comments about how such uniformity comes about. It's not that much of a different technology than the standard technology that was used by Mordell and by André Weil and by Faltings. But it's a relative thing. You start with this field extension, L over K, and you suppose that A satisfies the hypothesis of the theorem, and L over K is cyclic of prime order. Okay. Now, the first thing you prove is that that A of L has the same rank as A of K, as long as a certain relative Selmer group, and you have to define that relative Selmer group, vanishes. Now, that relative Selmer group lives in something that's clearly going to help for uniformity issues, because it has nothing to do with the L over K. It's just the one-dimensional cohomology over K of the L torsion points of the group of L torsion points of A. Now, this group, as I mentioned in the first lecture, is infinite usually, and so it's not going to give you any bound. And what we're looking for is not a bound here. We're looking for a straight zero of this. We're looking for a straight zero of this Selmer group. So what we're doing is we're going to define this Selmer group by local conditions, as mentioned in the first lecture. And you want these local conditions to vanish, and vanish quite often. And what's weird is that in the relative case, you look at these conditions prime by prime by prime, and there are certain primes. You go to our paper and you'll see we have an explanation of the structure of the proof at the first page. You'll see that there are certain primes that we call silent primes, and certain primes we call critical primes. And the silent primes give you a lot of room to move about. So when you ask for un-L over K, a field extension, the first thing we do is we say, we don't want a global field extension. We want a local field extension for every prime V. Now, you can't put together any old local field extensions into a global one, but what you can do is you can analyze the situation, because whatever field extension you're interested in will live in this very H1 of K, the same H1 of K A brackets L. Okay? Now, you play with it, and you see that let's say the freedom you're given by these silent primes allow you to do two things at once. That is to say, make the Selmer group zero and produce a whole bunch of local things that add up that come from a global field. Anyway, that's the technique that we use to prove the theorem. Now, there's uniformity in various directions and various with various well, I mean, anyway, recently we have this absolutely amazing theorem that if L is a prime number, the set of elliptic curves E over Q that are L diaphantic stable over K has density 1. And this is in a recent paper, which I have at the bottom of the slide. And I'll put my slides in perhaps some more organized form on my webpage, so you can take a look at it. So what are open questions? Let K be any number field. Do we expect, even in this, as I say, broader framework, that the average Mordell-Very rank for elliptic curves is a half? I think we do, but that's a question. And we might ask also, as in the paper of Park, Funen, Voigt, and Wood that I cited in the, lecture 1, that ranging over all elliptic curves over K, but with the J invariant a primitive element for the field K, and defining Bk to be the smallest number of smallest number such that there are only finitely many elliptic curves with Mordell-Weil rank greater than Bk. Is it true that Bk is finite, uniformly bounded with a bound independent of K? It may well be true, and that might be a great project, I think. Not so much to prove, but to prove that the heuristic that was developed by those authors might extend. There's a suggestion of that. But back to abelian varieties. We could ask similar Mordell-Weil uniformity type questions for abelian varieties of any fixed dimension. Might we hope for a broad extension of the LMFDB database to include such data, as well as data about curves of higher genus? And this has already been started as the entries regarding genus 2 curves over Q, higher genus families, and abelian varieties over FQ. Now, I learned in this winter school from Drew Sutherland, from Shiva, Aaron Asaf, and Taylor Dupuis, that things are moving really rapidly, more rapidly than I had known. See, as I say, there's an archive note of abelian varieties over finite fields. There's regarding torsion points on higher dimensional abelian varieties, there's Shiva Chidambaram's talk at JMM about that describes his work with Goodman that computes Galois action on torsion points, or at least gives an algorithm to decide whether Galois action on torsion points are full or not in genus 3 curves, in a certain class of genus 3 curves. And regarding abelian varieties, Drew has just given me the right to throw this on the screen, namely there are at least 63 torsion subgroups known to arise for geometrically simple abelian varieties defined over Q. And there's the list. To go back to abelian varieties themselves, how should one organize them appropriately for their role in arithmetic statistics? Again, in this winter school, Aaron Asaf mentioned to me this question, which is absolutely an important one. How in the world do you enumerate in an appropriate way so as to be able to get statistics? Abelian varieties, when they aren't enumerated as the Jacobians of curves. That already sounds like maybe a minor project, but it is a project. Okay. As I say, my last line here is I learned loads in this winter school. It's really a marvelous environment to learn things. Anyway, thanks AWS.
Questions?
Hello, thanks for the talk. What are some applications of this L-Diophantine stability concept?
Applications?
Yeah.
You mean applications of having Diophantine stability?
Yeah.
Oh, well, for example, it's really interesting to know that there are only finitely many quadratic fields that have the property that x1 of 31 is not Diophantine stable for that extension. What does that mean? That means there are only finitely many elliptic curves over any quadratic field you want. Well, yeah, except for there are only finitely many quadratic fields that allow for a 31 torsion point on an elliptic curve. Isn't that? That's an application. I mean, that I thought of as not only impressive in itself, but it's quite an interesting beginning because, after all, the gonality of 31 is 12. What do you do with something that you have I mean, suppose it works for the 12th, which I don't know whether it does or not, but there may be abelian subvarieties in the symmetric 12th power of x1 of 31. But how can you even think of the uniformity of it that every, my gosh, every field of degree 11 or lower just doesn't pick up any thing that you might be interested in at the time. You might, at one moment in your life, you might be interested in finding these elliptic curves with specific properties, and the uniformity that's offered to you by Diophantine stability is quite impressive, I think.
That's quite amazing. Thank you.
So regarding torsion on abelian surfaces over Q, what are some approaches, partial results towards uniform boundedness of torsion on abelian surfaces over Q, or some roadblocks to sort of do that?
For abelian surfaces?
Yes, boundedness of torsion.
Well, that's the thing. The reason for this lecture, there's subtext to every lecture, right?
I suppose.
Okay. The reason for it is to press for people to think about this. I mean, why abelian surfaces? Why not abelian, threefolds? These are interesting questions. They're not out of reach, at least in some form or other. One might begin to imagine proving serious, for example, finiteness theorems. Computationally, we're beginning to compute, as Drew did last night. Last night, that last slide that was attributed to Drew was a computation he made last night. So wait till tomorrow, we'll see. Yeah. I should also say, here's a thing where I don't know how you compute it. Maybe people here do. I defined, using that silly term, non-nearly elliptic curves. I think it's an interesting collection of curves. I mean, it's so simply definable, just as sim squared doesn't contain an elliptic curve. What could be better than that? So simply definable. And you immediately get finiteness. So, for example, for x0 of n ranging from 11, I guess, to infinity, you might ask, what's the statistics for sim2 of x0 of n being non-nearly elliptic? Well, whatever statistics you get an enormous amount of statistics of non-existence of quadratic n-isogenies. And I don't think the question of how many non-nearly elliptic curves among these modular curves, how many of them we expect. Do we expect only finitely many of nearly elliptic ones, or do we expect some sort of density? None of this has been, as far as I know, and there are people in the audience who might know more than me about such things. As far as I know, nobody's even looked at that. So it's, anyway, that's the subtext. Yeah.
Thank you.
Hey, over here in the front, in the very front. Yes.
Okay.
Hey, so I had a quick question. So when discussing, I think it was like the relative Selmer group, or whichever thing was embedding into like the H1 of the torsion.
H1 of K, L torsion. Yeah.
Yeah, and so I think you mentioned that this H1 is usually most of the time infinite, and so I wanted to know if we understood cases when this guy was finite.
Oh, never.
Oh.
Never, I think.
Oh.
What?
Oh, never?
Yeah, never. Except if A is the trivial abelian variety.
Oh, okay.
Yeah. Yeah.
Yeah.
So I said most of the time simply to be a little more homey than I think I should have been. Sorry. Yeah.
So you have these L Diophantine stable stuff for elliptic curves, and you're saying that there's a result that says the proportion of them is 1, right? 100%.
Yeah.
So for that's 0%.
What?
Do we know what kind of extensions? So the question is, for that 0% that are not L Diophantine stable, what kind of extensions do they have, right? What's the thing that's breaking?
Yeah, no, that's a good question. Yeah. I mean, since they're rare, your question, here's a way of putting it as a statistical thing. They're rare, just consider them as a family, and then what's the probability that even though they're not Diophantine stable, their rational points go up by a certain amount. These things have not been studied yet. They might be in the future, but yeah, it's a great question. I interpret your question as even more broadly. You're probably thinking every time you have such a Diophantine stable situation, the non-stable ones deserve their own statistics. That's the point of your question, yeah?
Okay. All right, let's thank Barry again for his lecture. Okay, and let's go ahead and thank all the speakers for their amazing